intensity in I, intensity in B, intensity in green, each one multiplied by its own coefficient. What is this coefficient? Is this door red? Definitely yes in this drawing. Door is red, so the coefficient in red is large. It will reflect a lot of the light unidirectionally. Here is a part where the direction to the light has an impact, times the intensity, how strong is the light coming from the headlight in R and in G and in B. And that would be the effect of one source of light. It doesn't like me. So when we have only ambient light, that's how the sphere looks like. And when we start to add the ambient light, we're taking the coefficient of the diffuse light to add on top of the, you have the two spheres over here. You wouldn't see them at all had there will be no ambient light present. We are adding some ambient light, which is unidirectional, so even the objects that are shaded from the light in the shadow will still be visible. And now on top of it, we'll start to add the diffused components. If I have one source of light, one headlight, I will multiply the intensity of the light coming times the cosine that we just mentioned. But this cosine might be negative. When will it be negative? If you're pointing the shape, but that's the back side of the shape. The normal to the shape is going on this way. And then it would be negative, and then you just don't add this component. Eventually, what we'll have is to add the total impact from all the sources of the light. If I have another lamp, I'll just add the impact from this lamp on the shape. So that the shape is seen where you add the sun somewhere here, and you see the nice pattern over here. And the reason, as we discussed last time, the reason that you see also the back side of the sphere is because of the ambient light. There is still some impact. Okay. And more and more you're playing with the Lambertian, with the diffuse part. And that's just what you probably know from mid-school, elementary school, maybe before, about why things that don't point to the face. Thanks. Yeah. Again, I'm not making coming to class mandatory, but I still want to know who is constantly coming, who is not. And okay, and you see the impact. We talked about the moon paradox. Why don't we see the diffuse Lambertian effect so much about the moon? Yeah, we still, of course, there is a dark side of the moon, obviously, and there is a front side of the moon, and you do see that region towards the equator, the sun is over here, obviously. Pieces after the equator becoming darker and darker, but you don't see much impact of the normal to the moon versus the sun in all this region. Why? Because it's not the normals are not uniform. They are not really pointing outward. I claim that the normal direction. It's not flat, lots of craters. Each one, or a lot of the craters, have a piece of the boundary of the crater that points to the sun and hence illuminated. Okay, that's old slide. We talked about it. And we talked about ray-sphere intersection. I just wanted to mention it again when we want to find the intersection with the billboard. You had it already in the previous meeting, and the intersection with the sphere. solving this quadratic equation. And now I want to speak about mirrors. I want to speak about mirrors because in homework 4, I'll ask you to implement mirrors. I'll ask you to implement a sphere mirrors, and we need some discussion how to do it. And the intention is that you could do things like, let's song it a bit. So here you have a few spheres and one billboard. In this scene, you see one billboard that is a chess, the chess board. You see 4 spheres that have ambient color, and you're using the ambient coefficient, the how red, how green, how blue it is, basically, and you're using these coefficients, just multiply them by the cosine of the light that hits the object. The direction of the light that we assume is white light contains all the R, all the G, all the B, as it hits the object. And you see that based on the normal to the sun is where the projector is, the point which is pointing towards the sun is highly illuminated, and it's becoming darker and darker as the normal to the sphere is changing. Now, you also see a sphere in the center that is shaped as a mirror. And as such, there is a reflection that you see because the blue sphere is reflected in the mirror, and you can see it. And the reason that I asked you in homework 3 and also in homework 4 to generate videos is that getting the 3D shape out there is much cleaner when you start moving the camera, start changing the parameters of the cameras. And it takes lots of time because it's recursive ray shooting. So I limit the resolution so it looks somehow crappy after all. But no, that's not what I wanted. Hello. So yeah, where did it go again? Okay, I did something wrong to it, but I think that the idea is clear. 4 spheres floating here. The camera is moving, while how do I keep watching the, how do I update the look at vector? That's where you see how it's convenient to do it the way I suggested. I want to, the camera is moving, it's actually moving across a horizontal line, and it's in what is the equation of this line. Oh, I mean, there is more than one option, but in standard coordinate system. What will be the equation of the line that the camera is moving on? Let's do it from the start.
Like a little X in the corner that you might be able to.
Yeah, I thought this X. Yeah. Why didn't I think about it? I was thinking that this X will eliminate my, but it still looks better here. So, similar scene, just higher resolution. So, took me obviously much more time. What do you think? What's our coordinate system? Let's do a quick review of homework 3 even. What, in this case, where is, yeah, where is U, I think, yeah. So where is W pointed in this scene? We'll start. Yeah, I know, I understand your answer. It's not, It's an answer to the previous question, and I'll get back to this answer. So in this frame that you see right now, this frame, billboard, which is chessboard, 4 spheres, and we are watching this scene. Show me X, Y, W, or U, V, W. W is toward me, right? W is pointing away from the scene, and where is the look at? What are we looking at? Probably the center of the mirror sphere. Right? So that's a look at, W going the opposite way. And under this coordinate system, where is U? Show me. U is going this way, and V is up. But makes sense. And now I'm moving the camera along the U direction. That is, I'm changing the U direction of the camera, adding to it the time times U. Hello. Adding to it the camera times U, but keeps looking at the very same center of the sphere. So that's the only parameter that I'm changing. Just the direction that you are looking at. And you see that the sphere is indeed a mirror. You can see the reflection of the billboard. How do I generate the reflection of the billboard, of the chessboard? I shoot a ray through my image. I'm holding the image frame, shooting a ray through the image frame until it hits the scene. If I hit a billboard, I leave it alone. You don't actually need in this homework to apply specular or diffuse parameters for the billboards themselves. But that was just because that's what I decided. However, there is one nuance here that we'll get back to it in a second. So I hit the billboard directly. So what will be the color that I'll assign to the corresponding pixel, the ray that hits it? Just the color of the billboard where the ray hits. With a bit twist that I'll tell you in a second. If I hit a sphere, on the other hand, then I'll take the color of the sphere, and I'll take the ambient color of the sphere, kind of cayenne, add to it the color in the diffuse part, which means that I need to know what is a normal at the sphere where my ray hit. Right? My ray coming from here, from the viewer, from the image plane, hits the sphere where the light hits, then the normal points towards the light, and getting pretty large highlight. As I'm moving across the sphere, the diffuse component is becoming smaller and smaller, explaining this darkness. Okay? You also see that these spheres are shiny somehow, metal-like or shiny plastic, which you'll generate by the specular effect that we'll discuss very soon. What do I do when my ray hits the mirror? Again, I need to compute the normal to the sphere where the ray hits it. Again, I'll need to ask, hey, sphere, mirror sphere. At the point that I hit you, a ray that hits the sphere at P, the center of the sphere is C. What should I do? I want to ask the sphere what is a normal to the sphere at P. How can I do it? I'll take, we discussed it, P minus C. P minus C is a vector that points this way, and for conveniently, I'll normalize it. P minus C, normalized. This will be the vector N. if it is, if I hit a non-mirror sphere, then I use this normal to apply the diffuse and the specular effect. Specular, we still didn't know how. If it's a mirror sphere, then what do I do with this ray? What do I do with this ray? Let's actually call it D. I look at the vector D, I look at the normal, and I'll figure out, based on the normal and based on D, where it is reflected. Because I still don't know for this pixel pi emerging from the eye through the image plane via the pixel pi that I need to decide about the color, I still don't know what is the color of pi. The color of pi, I was hoping that the sphere itself will have a color and then I'll know which color to assign to pi, but instead I hit a mirror sphere, so I don't know what the color it is. Instead, I will have to see what is a reflection of some object, if any, that hits pi at this point. So now I'm putting a virtual eye at p, shooting a new ray r, and if I hit somewhere a blue ball, now it's blue sphere, then the color that I'll assign to this pixel would be blue, based on the first object that I hit. Okay. So it's, what did I do in terms of ray tracing? I first shoot one ray, and now I shoot a new ray out of there. So I call the ray tracing recursively. Now it's a virtual eye at P, and it's a new direction that the ray is going through via R. And eventually the ray tracing will return for me the colors that I need to put in this place. And why is this recursive? Because this might be another mirror sphere, so you might need to continue it. And essentially it could be that it will be, you'll bounce between two mirrors infinitely many times, so I'll tell you what is the maximum depth of the recursion. What other effect do you see in the mirror in this frame? There is one effect that we did. We talked about diffuse, we talked about specular, we talked about mirror, but there is something else there.
Did we talk about the shadows?
We have not talked about the shadow yet, because when I hit a point on the billboard, probably will limit it at only where 4 points in the billboard. What do I ask? I ask here, hey, point, are you only in the shadow? And if it's in the shadow, then the color that I'll return for where my finger is would just be the ambient color out there. Ambient light exists anywhere, not occluded by anything. So even though it's in the shadow, I'll return the ambient color, which is normally what we just call the color of the object at this point. How do I know if it's illuminated? Then the intensity that I'll return will still be the ambient in this case, just much stronger. I don't play with specular and diffuse effect for the billboard, just decision. But how do I know if it's in the shadow or not in the shadow? I need to shoot a ray from this pixel to the sun. Why do you see the shadow of the sphere over here? Why do you see the shadow of the sphere over here? Because when you're trying to go from here to the sun, you will hit the blue ball, and hence you would decrease the intensity. How do I know if this point hits the sun or not? I use my ray tracer once again, but this time my virtual eye is on the billboard, and the direction is just toward the sun. Okay, so there is several components that we need to explain how to do. Okay, and the shape of the shadow is much cleaner in this case. Is this a point source of light or area source of light? Area source of light would be like the lamps over here that have covered by a plastic, by some frame, so you have an illuminated surface. Is a point source of light, or is this a lamp that has some volume? A lamp that has some volume.
Point source?
Point source, and that's because?
There's no fade on the shadows. It's either on or off.
It's a shadow without any shading of the shadow. How would it look if you have a multiple sources, or you have a lamp that has a volume? The boundaries would be much more fuzzy. You'll gradually move from being completely in the shadow to be completely not in the shadow, where you'll have a region in between where you see part of the lamp but not the other part of the lamp. Hence, multiple shades on the boundaries. So it looks in the sense very unrealistic because of this point, which is promo to our next topics of how do I decide really how much light is falling on a point if I want to get it a bit more realistic. I will shoot a few rays, because now my rays or the direction of the light is multiplied. But what, do I need to send infinitely many? What's the resolution? Should I send n by n? That's a point where you're saying, no, I just pick just a few directions and try to get to the light via this direction. But which directions do they pick? Well, people that took algorithms with me know that I'm a big fan of randomized algorithms. Essentially, at any point when you're designing an algorithm and you're not sure what is a right sample that you want to take, what is a sample of points that you want to take, just toss coins. Have a randomized, stochastic, distributed ray tracing that will be for a pixel, shoot a few rays at some random orientation and see what is the amount of light that these rays reflect to you. Don't bother with the whole gamut of all possible rays to all possible directions. Pick a sample of directions. Okay, so that was a promo to what we are going to cover in the next week or two. Shadow. Here's a light source. Here is a reflected light source, or a viewer that is sitting just here in the very correct place. Or we are playing pool, and here is my cue ball, and I want my cue ball to get to this point right here. Famous pool trick. How do I decide what is, if I can shoot my cue ball directly, then obviously I'll prefer it, but there is some obstacle over here. I want to bounce it from the edge of the table. I want to bounce it, the cue ball, from the edge of the pool table, or I want to ask if that's a mirror over here, I think the face of the mirror. Which direction is the reflection of the light? I'm a viewer right here. I want to ask at which direction will I see the reflection of the light? And the standard trick for all of it will be take the distance from the sphere, from the cue ball to the edge. That would be d. And now create a virtual ball or a virtual light source. How? Take this distance d and continue d, that is, go to d. In which direction should you go? In the direction that is normal, that is a normal suggest. Take this distance twice. This look at your location plus this distance again. And that would be a virtual cue ball, which is actually outside the pool table. Or that would be an imaginary light source that is actually in the other room, across the wall. Nevertheless, once I got this point, which I only need to know what is the normal of the surface at this point, once I got this virtual point, then here is the direction at which my viewer will see the reflection of the light. Again, I want to ask at which direction will the viewer see the reflection of the light? Answer, imagine that the light's coming d times 2 directions in this point, creates a virtual line. And now draw a straight line. Imagine that that's a source of light, but now there is no mirror anymore. Make sense? That is. When you're hitting the cue ball, imagine that your target will, other way around. If I hit the cue ball and I want it to bounce over here, I'll imagine that my target, which is over here, is actually on the other side of the cue ball, of the table, but where exactly? D times 2 location over there. Okay. So what do I know about bouncing from a mirror, once again? Well, not too hard. I know that the direction, if the viewer sees the lamp in a perfect mirror, that is, the viewer sees the reflection of the lamp, and the reflection of the lamp is, how do I generate the reflection of the lamp? Do my trick with taking it D and D again, so the virtual lamp is over here. What happens in this case? The incoming angle, the normal, this angle, here is the direction that you shoot the ray. That was the direction that you shoot the ray from the eye until it hits the sphere mirror, D. It will bounce, creating the same angle, theta, with the normal. This is theta, this is theta. A, B, I want to ask where do B see the reflection of A? Take this distance, D, continue D units in the opposite direction. So that would be A prime, and create a straight line, which would mean that theta equals theta, which also means, theta, I actually said it, shouldn't. Theta equals theta, this direction D vector, E versus the reflected. Now here doesn't stand for ray, it stands for reflected ray, creates angle of theta with a normal, theta and theta, which also implies that alpha equals alpha. Do I see reflection right here? Not yet. Now I see the reflection because I'll add some shininess to the table. So a ray that I'll do in the ray tracing process, a ray that comes from the eye via a pixel in the image plane, a pixel that you need to render. It hits the table, takes a reflected direction, going upward until you hit one of the spheres. Okay, and that will be the color that you assign to this point. But notice, the color that I assign to this point is not a color that I change the mirror itself. It's a color that I assigned to the pixel, which is part of the image plane that I generate, that you are playing with in homework 3. Okay. Ray tracing as opposed to ray shooting. Ray shooting, I stop the moment that I hit the object. Ray tracing will say now your job when you hit the object is not necessarily done. You notice that this object is a mirror. And we are going to use all of it when we'll speak about objects that are not mirrors, but have specular effects, like metal-like effects. It will be quite relevant. So trace the ray D from the eye via this pixel until you hit some direction, and now you want to generate a new ray R. How do we specify a ray? When I need to specify a ray, I want to specify, normally, the location of the eye, some point P, and I'll generate a vector V, and my ray will be the I plus T times V. Sometimes we'll prefer to normalize V, but not necessarily. The direction is what I care for. That will generate this ray. Now I need to generate the ray R over here. It's a new ray. I want to know what is the first object that this new ray hits. Again, it's not only to find if the ray hits an object, if this ray hits an object, it's also to ask, are you first hitting the blue ball or are you first hitting the black ball? Because the color of the first hit object is what the color that you'll assign to this pixel. Or you'll continue it recursively if you hit another sphere mirror. So I need to generate the location of the virtual eye, but the location of the virtual eye is exactly where my ray hits. That's a new source of a new ray. That's where I'll put, for a moment, my I prime. How do I find the direction of the reflection? I told you a long, convoluted story of imagining that the lamp is actually on the other side of the table in certain distance. Let's see algorithmically. How do I do it? How do I find this new vector R, the reflected vector? Claim N is a unit vector to the mirror where you hit. N is a unit vector to where you hit. And R, the reflected direction, would be D, this direction, the direction from the viewer to the eye, minus 2 times D times N, dot product, that's a scalar, times N. Very simple equation, but let's explain. At least notations-wise, everybody understand? D is a vector, N is a vector, therefore I can compute their dot product, which will give me a scalar, multiply it by N once again, which will give me a vector, and subtract a vector by a vector, you'll get a new vector R. People, questions about it? My next 2 minutes is just to prove that it's working. But algorithmically, you all understand how to implement it, how to program it. So let's prove it. N is a normal vector. In this case, I'll rearrange my world so that if I don't care how it's arranged originally, but I'll rotate it so N will point vertically up. Just rotate the whole world, just for the proof, not algorithmically. I just want to convince you that this claim is correct. So in this case, I rotate the world so N points upward. But of course, there will be cases where my mirror is actually curvy, and I'll still want to compute the reflection from the sun to some arbitrary points of the mirror, the reflection from the sun to an arbitrary point of the mirror, where is the reflected ray is going to. And every point, I have the normal to this point. How do I compute the normal? We discussed it. Normal is E. How do I compute no, that's not the normal, but the normal would be bug. The normal would be P minus C. Okay, now I understand why. Okay, so I rotated my world, so locally, of course, if it's a sphere, then every point has a different normal, but I'm asking about this particular ray that just hits my surface at this particular point. So I'll rotate it so n points upward. Now, D has two components. Vector in the plane, I can represent D as it has a x component and it has a y component. If you think about D as a velocity speed, you're shooting a basketball, wants to bounce a basketball through the floor, then the velocity, the ball that you shoot to the ball, have the dx, which would be in this case the horizontal, how fast your ball moves from right to left, and it has the vertical component, how fast it moves up and down. And now assume that there is no gravity. No gravity, so the speed doesn't change where your ball bounces. And how can I express the components, the speed of the ball after it bounces from the floor? And assume that it doesn't lose any energy. Perfect ball. Doesn't lose any energy where it hits the wall. What would be, if you know what is dx, horizontal speed, dy, vertical speed, what would be rx and ry? Help. Perfect ball, no gravity, keeps bouncing from, I'll get a bit other involved, because that your chance of class participation does affect the eventual grade that you'll get at the end of the class. I had a few cases in last semester, yeah.
X is the same and the Y is opposite.
X is the same, right? The speed that my ball moves horizontally, again, perfect ball, no gravity. Speed that it moves horizontally doesn't change where it hits. What about the speed that it moves downward? It will be exactly the speed that it moves upward. So the r of x, speed in x, stays the same. It's just d of x. This component is not influenced by hitting the wall, hitting the floor. But r of y, r of y is minus typo, minus d of y r of y is minus d of y. If d of y was going downward by 3 meters per second, then r of y is going downward by minus 3 meters per second. That is, up by 3 meters per second. So r of y is minus d of y, which is what? R of y minus 2 times r of y. That would be a very awkward way to write it. But what is r? How can I understand from just knowing where is r and from just knowing where is n, what is r sub y? We played with this game many times. I want to know what is the x component, what is a component of a vector in some direction. I should multiply the vector by this direction. Once again, if I have the x, y coordinate, and I want to ask in the x direction, x vector, which is 1, 0, what is the value of this point in this direction, then take p, which is x prime y prime and compute the dot product of p and compute the dot product of p with 0, 1, and then you'll just get the x coordinate, the length over here. The projection of this point across this line. And this expression doesn't care at all that x is horizontal or vertical or arbitrary direction in 2 or 3D. You have to do it, by the way, with alpha and beta on the billboard, if you didn't notice, to compute alpha and beta, to compute the coordinates of the point on the billboard. So what is, therefore, r of y? R of y is, I want to know what is the projection of this vector, not on the x direction, on the y direction. So I'll multiply n times r. That tells me what is the value in this case. And I'll take r of y minus 2 times r of y, which proves our claim over here. Okay, and everybody understand y is 2? Where is this vector points to? Where is the vector in my image? Where is the vector d minus n dot product d dot product n? This vector, where is this pointing to?
Would it be the horizontal component, like the distance from the x coordinates?
You have a medicine ball. You have a ball that has no bouncing. What happens to it? It bounces over here, and it continues with the same horizontal speed, but you completely killed the vertical speed. You just zeroed out. You took the vertical speed minus the vertical speed, so the vertical speed is 0. So essentially, what you'll get is just in this case, just the vector, which if n pointing downward, it's dx, the x coordinate of the incoming vector, and 0. That is, you're moving tangents to the surface if n is not vertical. But now I am taking 2 times this number, so I'm just bouncing in the opposite direction. All good. Okay? So now you know how to compute the color of an object if the ray that you are shooting from the eye, the origin, via a pixel d, one of the witness points that you generated on the image plane, shooting it. You hit a surface P. You know if it's sphere, the sphere is given to you by telling you where is the center and telling you what is the radius. You solve this quadratic equation to find where is P, the intersection point, and now you know what is a normal. And now you can generate R. You can generate a R that will be the vector from P minus C, normalize it and do this trick, and this vector will bounce in this direction. So let's go to my GeoGebra despite the bug. So the reflection would be in this direction. Okay, and I'm just using the very same trick, except that when I moved from a flat mirror to circular mirror, I didn't change it. So bug on my expense. We are good with mirrors. You know now how to implement billboard in your homework 3. If I'll ask you implement flat mirrors, you know how to do it. You'll just need to call your ray tracer once again. When every time that you hit the mirror, generate a new ray. There is mirror and another mirror. And and here is my eye, and here is one of the pixels that I want to know what is the color of this pixel. What happened to the ray bouncing, for the ray that goes from my eye via P? It will hit the mirror and bounce, and bounce, and bounce, and bounce, and unlimited, so you need to limit the maximum depth of your recursion or else. At least if there are one mirror, it's fine. If there are two mirrors, then you are risking something. Yeah?
What value would you give the pixel if the ray hit its maximum recursion depth?
Default. You decide about the default, or I'll tell you what the default is in CLS. Like in the video, there was some background. Green here was a background of the every pixel that I decided that the background is green, meaning that if I shoot away and I don't have any object, I decided that it's green. Completely arbitrary. Okay, now let's talk about the specular reflection. Specular reflection would mean that you see this shiny point right here, this shiny circle right here, that is very much related to the mirrors that we see. To mitigate the impact of the bug, instead of changing it right now, let's just increase the curvature. So now my mirror is almost flat. So you almost don't see the bug. That N is not pointing. So if the curvature would be like, the bug is at N always, points vertically. But in this case, it doesn't have much impact. So now, you see this point very shiny. It is important to render it. I think that yes. Check the difference here versus here. What gives you more feeling that it's alive, and you see why it's 3D? Yes, specular is important. Let's continue. Let's remind you this example. You have the same shape in this very, very classic 4 images. On the left, only ambient light. What do you see? Only the silhouette of this shape. Now I'm adding the diffuse effect. Now I need to know where is the light. This image, I don't care at all where is the light. Only ambient. Doesn't have direction, doesn't have location. Here I cared about the location of the light, but I don't care at all where is the viewer. Now I'm adding the specular effect. Specular effect would mean I'm adding the specular air spots at certain location. And what are these locations? These are exactly the point where you'll see the reflection of the light had this object be perfect mirror. It was convoluted sentence, I'll repeat. Imagine that I take it and coat it with silver, so it becomes perfect mirror, this object. There is 1, 2 sources of light in this scene. Where do you see the reflection of the light at this point? Exactly at the center, since it's point of light, exactly at the center of these spots. Okay, and I just take the value of the spot via the specular reflection. Here they are. By the way, they don't care at all what is the ambient color of the object. They said if the light is white, I'll return it in the same amplitude as light points, regardless of the ambient color of the object. Always white. Take these shapes, add it to this one, and now you see the resulting shape that looks, to my taste, much happier. So let's see how we compute this point. So we talked about finding the exact location of the reflection. And now there is a specular reflection that would have behaved just here as if it's perfect mirror. But if it was a perfect mirror, then of course, and it's a point source of light, then its reflection should be a source. While this spot has some smearness, some meat in it. It's not a point reflection. Let's see how to do it. So we know how to find the reflection, and now we are using, we are asking, can I generate the specular effect exactly? Answer, probably not. The result that you see the specular effect is that a lot of the local normal, the surface is not completely flat, but a lot of the pieces out there are behaving because of physics. But they have all different orientation, and it would be totally impractical to simulate this effect accurately. If we'll have time, I'll show you how to simulate it a bit more accurately for metal objects. But still, it's simulation. It's generating synthetically something that looks like. And for this, we are using the Phong formula, Phong effect, Blin-Phong effect. But Blin-Phong is not the shading. There is a specular shading. Specular is a physics effect. Blin-Phong generates something that looks like the real thing. So how does it behave? I will look at I'll move P across the surface. Here is the direction of the light. Or equivalently, when I'm staying at P is one of the points over here that I want to generate. P is one of the points here that I want to generate. As I'm moving P, let's imagine that it is a perfect mirror. When will you see the reflection of the sun in this mirror? Not hard. It's a perfect mirror. Where do I see it? I'm looking at the angle R, at the angle alpha. Alpha over here is the angle O. Let's imagine that my ray has perfect reflection R from the surface. And also, let's look at a vector, called it V. The vector from P points on the surface to the viewer. Viewer is here, sun is here. If I didn't mention it, in diffuse effect, the location of the viewer is irrelevant. Specular effect, as the viewer moves, the specular spots move, even if the light stays the same. Look at the vector V to the viewer. Look at the vector L to the sun. Look at the reflection R between from the light of the sun versus the location of the viewer. Where do I see, at which point, what point on the mirror, which point of the mirror do you see the reflection of the sun? Goes back to the drawings that we had earlier. Where do I think about alpha over here, the angle between R, direction of reflection, versus the direction to V? This is a piece of the mirror where I look at this point, what I'll see is the reflection over here. What's special about the point where I do see the sun? The direction of the reflection direction points directly to the viewer, right here, correct? Alpha will be 0. In alpha, the angle between V and R, alpha will be 0, meaning that the viewer is exactly at the point where the sun has a perfect reflection toward the viewer. Meaning that when you're gazing, when your sight is concentrated on P right here, and P stands such that incoming and outcoming angles are the same, then you see all the intensity at this point, which means you see the sun reflected at this point of the mirror. Make sense? If alpha is different, and it's a perfect mirror. Alpha is non-zero. You and everything else is dark. All these points will appear completely black. All the points besides the point where alpha is 0 of the mirror will be completely black. Okay, so what's happened, what's interesting about the diffuse reflection? You see the center of the spot. You see the center of the spot, which is exactly where you have 100% reflection. The strongest point, because that you see the reflection of the light source. But how come it's not just a point? The normal changed just dimmer and dimmer, but it's still non-zero. Again, in the example over here, when we isolate the specular spots, there is a center of the spot, and when you're going just slightly away from the spot, you still see something. And Fong said, I want to find an easily computable method to compute it. To say, you'll see 100% over here, and now you'll move P and alpha. Alpha, everybody is good with the definition of alpha. Look at the direction of perfect reflection. Look at the direction to the viewer. Alpha is the angle between. If alpha is 0, you need to see 100% of the reflection. And I don't care at all what the color of the mirror itself, but the color of the object itself. If alpha is non-zero, then the larger alpha is, the return intensity should be smaller. So what should we do, or what did Fong suggest, and it caught up? Fong said, look at the cosine of alpha. Cosine of alpha, so the So Fong suggested to use cosine of alpha. Why? What's the justification of using cosine of alpha? Well, it means that it's a function that is equal, because cosine of alpha equals 1 when alpha equals 0, and then slowly decrease below 1. That's one reason. And the second reason is that how do I compute cosine of alpha? It is cosine of, help. I don't like computing cosine directly. It involves a lot of arithmetic, or looking at, or pre-computer it was looking at tables of cosine. You don't need it here. What do you do instead? Dot product of V, the vector of the point, dot product with R. That's exactly the cosine. So that was the other reason, because you can express it as just a dot product. You do have to compute R according to the formula that we had before, and I'll show you a shortcut in a second. And it works for some surfaces. But other surfaces, like closer to, more closer to, so what will cosine looks like, to remind you? X, and here is y, which is cosine of alpha. How does it look like? Here is 1, 0, and 0, and the cosine will do something like this, and goes down gradually. And it works for some surfaces. But for other surfaces, the closer you are to metal, then it will not work because it gives you the sphere, which will be somehow a region of the specular spot, which is somehow too large. So Fong, or Blink-Fong, suggested an improvement. You know what? Decide about a parameter m, the exponent of the Fong, and you'll decide based on the material what is m. So write some number m over here, which does what? When alpha equals 0, cosine of 0 is 1, and 1, no matter to which exponent, will stay 1. And still here. What happened when alpha is 0? Of course, when cosine alpha is 90 degrees, cosine is 0, and you don't see anything. It's still 0. But for intermediate values between this and this, your new graph, if m equal 2, then a cosine square of alpha would be much closer to the center. You're shrinking the graph to the center. Therefore, m equal 2, m equal 3, and so on. So back to our simulation, what you'll see is that I put on every point here a circle, and the size of the circle is the radius of the circle that I put on every point would be how much of the intensity you'll generate according to Fong for this point. If I put P at this point, then the radius of the circle is what's the value of cosine alpha to the power of m. What will happen when I'll decrease m? When I'll decrease m, then the decay, notice that the sphere is very large. It's a very small portion of the sphere. Or the sphere is actually a flat plane, same deal. What happens when I decrease m? Then I'm moving back from the black to red. And it means that many more points will have a lot of reflection. That is, the size of the specular spot will decrease. What is the reason of the specular spot and why does it have boundaries? It is because as I'm moving along the radius, I'm not anymore at a situation where the incoming angle is the angle to the viewer, ignore the normal. I have the incoming angle and I have the angle to the viewer, and as long as this angle and the angle to the viewer are not the same, then the cosine will decrease, obviously, and that's why the specular spot will be much more concentrated. It doesn't behave as a mirror or as an approximation of the mirror that you'll get for various materials. When m becomes larger and larger, it means that the specular spot is now much more concentrated, right here in the middle. Cool. So that's a reason for the exponent of m, and that's why Frank suggests take the cosine of m, cosine of alpha, which would be the cosine of alpha to the power of m. But that implies that I need to compute the reflection. And there was a question, can I get away without computing the reflection? Not that it's hard to compute the reflections that they compute are, but there is a cute shorthand. What Fong also suggested was let's compute beta. Or before beta. Let's compute age. What is age? Age is L plus V normalized. L plus V normalized. V, L, direction to the viewer. So now I just have two vectors, L and V. And I want to ask what is cosine of beta, where beta is beta.
If you
H plus L plus V, yes. L plus V divided by L plus V. Yeah, thanks.
That says B times
Still not an L.
Oh, sorry, so it's L plus, H is L plus V divided by L plus V. Yeah, ADHD. Completely. Okay, so that's this new vector H. And look at this angle beta over here. What can I say about beta when I'm moving P? What is the relationship between alpha and beta? Alpha alpha, 34 degrees. Beta, what is beta? Beta is the angle between H, this new vector that I generated, and the normal. What's the relationship between beta and alpha? Relationship between beta and alpha, 34, 17, 17.3, actually 34.6. Give you another sample point. Yeah, alpha and beta are the same, except that one is half of the other. So what Fong said is, you know what, just use beta instead of alpha because it's easier to compute. So what is beta? Take instead H, which is plus 3 normalized, add to, which is what? It's the bisector. H points is a bisector between L and V. And where do you see a specular spot? Where is a bisector of L and V? When the viewer, you see a specular spot, if once again, when it's a perfect mirror, you'll see a specular spot when the bisector between a direction of the sun and the direction to the viewer points exactly to the normal. Then beta equals 0, and then alpha equals 0. So take this vector and take this vector beta, and again, raise it to the power of m. If one is half of the other, it doesn't really affect by much the effect that you see. And that's the proposal. And now, what is m? How do you decide about m? It's up to the viewer or up to the properties. But that would be the effect when m becomes larger and larger. Back to the slides. So now you know how to generate the Fong effect. So Fong, sometimes you'll hear about it as a Fong shading, but it's a Fong visualization or simulation of the specular shading, but we'll just call it the Fong shading. So Ls, the specular coefficient, would be, and now you can decide that you don't want it as white, you give different coefficients. That's K of S is something that you feed into your visualization part. MATLAB / processing / whichever way you want to visualize a graphic. Part / OpenGL. You can generate KS, again, 3 numbers, RGB, times what? N dot product H to the power of, it's not M, it's P. P will be the specular effect. And let's see images where what is the impact of P. Okay, now this number can be negative. So you are taking the maximum of 0 and this number. And that's that would be what's the percentage of the reflected, of the energy that comes, the intensity of the light that comes, how much is reflected in this direction. So you take the intensity of the light that is illuminating the sphere and multiply by this number. And that's how you generate the specular spots. Okay, and you see it over here, and in the next image, you see the impact when I'm making P larger and larger, the specular spot, of course, becoming more and more like a perfect mirror. Perfect mirror, you'll just see the light as a single point. Smooth surface, more plastic, you'll have a large specular spot. Metal sphere, it will be much smaller. And of course, when Ks when Ks decreases, more and more light is reflected. And this is a hack, but that's okay. That generates something that looks reasonably. Putting all of the effects together, what I shoot away from 1 pixel in my image plane, it hits a point, I need to decide what will be the intensity of this point in RGB, with 3 separate equations that you see over here for each channel. Light 1, light, let's do it there. Light 1, and light, another lamp over here, light 2. What do? What is the intensity that I'll assign to this pixel? Or actually, the intensity that I'll decide that this pixel reflects, and if I see it, that's of course the intensity that I'll assign to this pixel. It would be how much ambient light is reflected, and there are 3 numbers. The object is red, then only red light is reflected from the object, meaning that K ambient in red will be 1, and K ambient in blue and green will be close to 0. Add to it what's written inside this big sigma. Add the effect of, go to the first light. The effect of the first light. What is written here? How much diffused light is reflected. How do I know how much of diffused light? There is a coefficient times the incoming light. Incoming light from what? There is I here. You're summing it up for the first lamp and for the second lamp. Each one has a different intensity and different color, different intensity in each channel, RGB. Intensity in this channel, I times the coefficient, times, what is this? N. N is a normal at this point. We have N already. Dot product Li. Why do I have I at this point? Because it's a normal that I show the Li is the direction of the light, L1 and L2. L2 is a vector that points to the second light. L1 is a vector that points to the first light. I sum it up. Makes sense. I just accumulate the light from the different lamps, provided that I see them. But it's diffuse light, diffuse effect, so I multiply by cosine between, cosine of what? Normal or to my surface, point toward you, and the no direction to the light. And dot product Li, that's the cosine of the direction of the angle of the light versus how do I hold my surface. And again, it could be negative. So if it's negative, we don't subtract light. Plus what's written here, don't add negative, times N times age I. Age I, because we have the L, age is what we had in the previous formula, and age, remember, had the direction to the light. Direction to the light in each case. So age to the light I, dot product N, all of it to the exponent of P. And now, since you're accumulating positive values, it can easily be more than 255. So unless you want to do HDR once again, then you'll just say if it reaches 255, I'll keep it as 255. No point of pushing it further. Don't let it overflow. Okay, and that's how you have the whole 3 effect. We are done with having the whole 3 effect. Again, the whole 3 shading effect, specular, ambient, and diffuse. Questions? Everybody fully understand? Perfect. Thanks. See you. Any question on homework? Homework 3?
I had a question. Is the distance to the image plane dependent on the FOV angle you give us?
Yes, but there is more than one solution. It's combination of, for a given angle, you can decide on any distance that you want, but remember that then the witness point, the pixels, should be more spread apart. I suggested to take, if you're doing what I suggested, but you'll find people that will argue that other parties, it's not correct or incorrect, but you'll find other opinions about what is convenient. If you decide that the height or the width of the image plane it's wider than higher, you can assume that the width is larger than the height. But if the width, if I look at the height and I suggested decide arbitrary, you can decide about any height. Decide that the height is 2. So the look at vector go through 0, 0, and then D will follow. D is 1 over tangent of alpha half, where this is alpha, so this angle is alpha half. And that's how I suggested to do it, and the rest of the formulas follow this part. But the first time that I implemented it, I found it more convenient. I got annoyed that I need to get to such a small number to generate all the pixels, and I wanted to use u as an integer. So I put my board at a direction, so u was an integer, so distance was depend on, the length was a number of pixels.